Yes, so my name is Ville Tuulos. I'm a CEO, co-founder of Out of Bounds, where we continue developing Metaflow, ML, AI infrastructure in general. I used to lead ML infrastructure at Netflix before, and that's of course where we started Metaflow. And so we have been doing this thing for now a good number of years. Actually, I wanted to start with the kind of a bit of a perspective here. So starting with this question that how does a tech-savvy company overall do compute, or how have they done compute over time? And of course, starting with the very obvious, it's always fun to take a bit longer-term point of view, is that if you go to the very beginning of computing, way before Python, of course you did punch cards, not many options there. Interestingly enough, maybe in 70s, 80s, you started having these mini computers, which was this idea that instead of having a room full of computers, so at least you could have something that maybe fits in a single office, and then you can do your data processing there in that environment. And now an interesting thing is that then maybe at some point in the 80s and the 2000s, if you were a somewhat of a serious enterprise and you wanted to do data processing, there were a good number of providers like Teradata and Oracle and others that sold you these database appliances, actually a rack full of computers that were fully integrated for data processing and compute and so forth. And I remember when I used to work a long time ago at Nokia, they had a big Teradata warehouse where you could run your compute workloads, and of course it was a very special, precious enterprise environment where you could do these things. And it was, on the one hand, of course, as you would expect from enterprise hardware, it was very reliable and very tightly curated. But the big downside was that also it was extremely limiting and didn't, of course, leave many options for any kind of experimentation or new kind of workloads or anything of that sort. So now the kind of really the interesting thing that happened then, in the early 2000s, some of you may remember that Google published a paper about this paradigm called MapReduce. I think it was 2004. And then it took a couple of years, I think around 2006, 2007, Hadoop, the most popular open source MapReduce framework was released. And then I think as an industry, and I'm sure that many of you remember as well, we spent maybe at least 10 years deploying increasingly large Hadoop deployments and then using the MapReduce paradigm. And I think one reason why it was so exciting for many people at the time is that if you contrast that to what existed before with these database appliances, now suddenly we were in this environment where we could, well, first, handle much more flexible workloads. And also there was this amazing idea that we could use commodity hardware. Instead of going to one of these expensive enterprise vendors, we could just get off-the-shelf computers, rack and stack them in these clusters. And there was also this promise coming from Google of having this infinitely scalable horizontal compute that as our data sets grow, we can do more and more just by adding more machines. And then also we had this really nifty compute paradigms like MapReduce that supposedly made certain things easier. So I think that although now, of course, many of us may kind of remember having not so great memories how hard it was to actually do many of the things that are quite standard these days. The big benefit was that it definitely was a jump forward from where things used to be in the past. Now, of course, the other big development that has been happening, and of course there's a certain overlap here as well. Of course, people have been doing cloud way before 2017, but really, if you think about that, your average tech-savvy company, it took a good number of years before cloud really became mainstream. But then there was this idea that, okay, now we can actually start scaling in the cloud instead of building these ever-increasing data centers and building our own racks of machines. And now, I guess what's really interesting here and kind of really the motivation for this talk, this is not just doing a kind of historical perspective on what has been happening, but also equally much about what's going to happen in the future. It's really interesting to see that there is actually very much a shift happening now between that early days of the cloud and of course Amazon and EC2, that was pretty much the OG, the first cloud that was available. And if you look at the landscape today, it is much more diverse. Of course, obviously, we have three major cloud providers. We have AWS, we have Azure, we have GCP. But in addition, we have many specialized providers, let's say, you need GPUs. You can go to CoreWeave, you can go to Lambda Labs. We have even specialized hardware, of course, coming from NVIDIA, AMD, Cerebras, and so forth. So it's a much more diverse landscape than ever before. And now one thing that's really useful to kind of also consider, like in this perspective, is overall like the amount of compute that like we as a humankind we are performing. And of course, like in the very early days, I mean, only very few companies even could afford a computer. So honestly, the amount of compute performed by the humankind was so small that it's kind of not even visible here. And like even in the early days, still, I mean, like in the grand scheme of things, like there wasn't much anything there. I think that like really like things started taking off, like with the kind of this like a big data boom, like kind of since the early 2000s, and of course the cloud is now happening as well. But like really the kind of the major and this is of course like a big prediction, like what's going to happen in the future, is that there are like a certain things that are really like driving the compute. And I think like there's a case to be made that like we are still in the very early days of the compute boom. And now it feels that, of course, like, oh my gosh, we are doing so much more than before. But as you know how things go with the exponential curves, I mean, it is definitely the case that we are doing twice the amount what we were doing like just a couple of years back. But I mean, like we will be doing twice more and so forth for years to come. And now, like when you actually like think about that, like what are we actually doing, and like what do these tech-savvy companies actually compute? One thing that's absolutely like worth noting is that for the longest time, like probably since the late 70s or so, pretty much most compute workloads, of course, like putting some like a supercomputing workloads aside, I mean, but the most normal mainstream companies, like what they have been doing, is pretty much like a run things what I call like SQL-ish, meaning that, of course, let's say like during the Hadoop boom, I mean, there was the whole NoSQL movement. I mean, it wasn't exactly SQL, but I mean, it's all these like a data processing operations, selecting, projecting, like massaging data in all kinds of ways, which like, again, like we are kind of back to the starting point again, like very happily using SQL with Databricks and Snowflake and whatnot. So that has been kind of the base load like for the longest time. And now, of course, like this is like probably not surprising that like the new thing, and I think that this is like really quite exciting that for the first time in many decades, there's actually something different than like running this like a data processing in different forms. Maybe, I mean, even like a MapReduce was just like a different twist on like kind of doing something that's SQL-ish. But now, like with the LLMs and so forth, like we have a whole new workload that is driving massive increase in the amount of compute that we want to perform. And it looks very different than what we have been doing in the past. So now just like a quickly motivating, like, because I think it's also like this helps to understand some of the technological shifts that are happening. So the first question is that like, why did we actually like move like from this horizontal scaling MapReduce Hadoop world in this like scaling in the cloud? Some of you may have seen this paper, like really good paper. You should look it up. You can Google for the name Scalability, but what at cost, which like really like is very like a concise point that they are making, is that like although you can have these horizontally scalable systems like MapReduce, oftentimes the performance can be actually worse than what we have in corresponding single node systems, just because of the networking overhead and the unoptimized implementations and so forth. And just to give you an anecdote, and like a really concrete example of this is that, for instance, like when I used to work at Netflix in the early days, like this was already many years ago, Netflix had their own distributed implementations of number of machine learning algorithms running on Spark. And they were proud of the fact that they were able to run larger scale machine learning models than pretty much anyone else, like thanks to these custom implementations. And then in 2015, TensorFlow was released. And of course, in some ways, TensorFlow is a Python framework. But of course, like the whole like a key to TensorFlow is that it actually is very high performance implementation utilizing GPUs and so forth under the hood. And now at some point they started comparing these distributed Spark implementations to this single node Python process that is, of course, now leveraging GPUs and so forth under the hood. And this single node implementation in many cases was able to beat the performance of the distributed system. Exactly kind of going to the point of this article. And of course, this was like really quite surprising, since for the longest time, like when we were in that horizontal scalability world, I mean, the idea was that that Python is just way too slow, and like in order to really do things at large scale, in order to handle big data, you need this like a little bit more high performance languages like Java, and like you need to distribute the workload and so forth. But I mean, that landscape started shifting. And also, like with the horizontal scalability, the idea was always that it's such a beautiful idea that you can keep adding more machines in your cluster, and things just become magically kind of faster and like more scalable. And although this idea of vertical scalability had been around forever, especially with those appliances, there was the feeling that, oh, but anyways, I mean, you will hit the limits of vertical scalability so fast, and it's kind of expensive to buy bigger Oracle boxes, and that's why horizontal scalability initially was so appealing. But now the thing with the cloud, and what this chart shows, is this actually goes back to 2006 and like kind of continues until 2019. So this is I should update this chart now with the latest developments here as well. But what it shows you is that it shows you what's the kind of the available memory in the largest available general purpose EC2 instance in the AWS cloud. And actually, like when AWS started, they only had these M1 small instances with 1 gigabyte. The largest instance you could get in EC2 in the early days was only having 1 gigabyte of memory. And then like a couple of years after, they released a machine with 15 gigabytes of memory. So of course, a massive increase there. And again, like a few years after that, they released this machine like with 68 gigabytes of memory. And now like this thing kept going, so that over the next, how much is that? Like over the next 13 years, the kind of the largest machine had 768 times more memory than like when they started. So pretty much exponential growth there, which meant that like anybody could go in like and click a button like in AWS and get the machine with absolutely crazy amount of memory. And this was back in 2019, and even today, like kind of having a box with 700 gigabytes of RAM is capable of handling like pretty decent sized data sets. Now, I mean, just to illustrate the point, like this is an example that I have given in the past as well, is that if you consider this data frame like a NumPy matrix, where you have on the rows, you have, let's say, like kind of the members of Netflix, and then like you have a bunch of features, bunch of information for every member of the company, and you encode this as bytes. What's really interesting to consider is that like that's the amount of data required to keep all Netflix members in memory is like shown here as this red area. And of course, like Netflix in the early days was growing really rapidly, like let's say starting from 2008, like a growing. But like, let's say like if in this data frame you use 1 byte like for every column, and you had 1,000 columns, what it means is that like kind of you could have get all the information about all the Netflix members conveniently in a single NumPy matrix, like all the time. I mean, just because of the fact that like the kind of the compute capacity was growing so much faster than like this, like a fast growing service at the time. And now, of course, you could say that, well, I mean, maybe 1 kilobyte it's not enough, but I mean, let's kind of consider the case where you have 3 kilobytes per member. And even in this case, I mean, despite like some kind of periods in time, like most of the time, like you were able to even keep this larger data frame in memory, like on these instances. And of course, this development, I mean, honestly, like kind of it's even easier today, unfortunately, in a sense that like Netflix hasn't kept growing quite as exponentially, but the instances keep getting bigger and bigger, and of course, like efficient in all possible ways. And what this says is that like one shouldn't underestimate like the amount of kind of the capacity and the resource increases that have happened, like even like within a single box in the cloud. And this doesn't even take into account the GPUs, which totally again changed the picture. Now the other interesting kind of thing to consider here is that like, okay, so now we used to have this like a scale in the cloud for the many years, and so we still do. But now like I would argue that like we are even like moving to the next level, which is that the landscape of just like running everything on AWS, like what we used to do with the Netflix, I mean, that is even like getting much more diverse and heterogeneous. And there are a couple of reasons like why this is happening. Well, I mean, one overall like trend is that like when companies were barely moving to the cloud, everybody did the simplest possible thing. I mean, like this was a new thing. I mean, that the system was very immature. They didn't afford like many options anyway. But overall, like kind of more and more cloud users are getting increasingly sophisticated about their usage. And like with that, they're also like becoming very sophisticated about how they think about the cost of using these things. So the original idea was that, well, instead of having your big own data centers and like your own people maintaining these clusters, it can be more cost efficient just to move everything to the cloud. And in many cases, that is very true. But then also there are different ways of using the cloud, and like the simplest possible way of using the cloud is absolutely like not the most cost efficient. And now increasingly, like people are getting like aware of this. And like this is funny enough a picture like from the AWS reInvent talk, keynote that just happened was last week or the 2 weeks before. where now AWS itself is very much like, due to the market pressures, like kind of really like putting forward this idea of like doing things in a very sustainable and cost-aware manner. Now, the other reason like why things are getting more heterogeneous is obviously the fact that there's simply more competition. And like it used to be that AWS was way ahead of everybody else, arguably, maybe it still is, but Azure, GCP, many others, I mean, they are absolutely becoming viable options. So it's of course like good for the users because there's more competition, more options, like more opportunities to also kind of leverage like the different options however you want. Now, also like a third development that has made this whole like a hybrid setup and more diverse setup more feasible is actually Kubernetes. So it used to be so that if you built your systems using AWS native APIs, you were of course absolutely locked in on AWS. It was impossible to move a system built specifically for AWS to Azure or GCP. But now, if you build your system natively for Kubernetes, you run it in EKS, you run it on AKS, on Azure, or like you run it on the whatever, like a Google Compute Engine on the Google side. So actually, like you can actually start moving between different systems. You can actually start building these more like hybrid deployments, of course, including on-prem more easily. Now, another thing, and of course, like a very relevant for everybody here at the PyData conference, is that the PyData ecosystem by itself has been getting like a very like mature, like which is super exciting. So it used to be so that we had NumPy. Of course, we have had NumPy for I think a couple of decades now. And also like we have had pandas, but I mean, of course, especially with pandas, the performance wasn't always there. But now over the past, I don't know, like a four years or so, like we have started getting a much more mature ecosystem of very high performance libraries. Of course, the Apache Arrow providing like many low level capabilities, like alternative data frames, like polars. What's super exciting that like we can even do SQL now thanks to things like DuckDB, and we can build enterprise grade data lakes using things like Iceberg, and then mix and match these different tools, which means that like we have way more options for choosing the best tool for the job. So in contrast to the days when like, let's say the only option was to run everything on Hadoop, suddenly like if let's say your data fits in memory, like you can use DuckDB and like maybe you don't need anything distributed. I mean, it's going to be beautifully faster than anything else that you can do. And now, of course, like absolutely like kind of the crazy development that has happened this year is this massive explosion with the AI and LLMs. And this is a like a fun projection like about the cost of training the largest scale AI models, and there are projections that training these AI models like will require so much compute that it way surpasses the projected US GDP. Well, I don't think that like we ever like quite get to that point, but it is absolutely obvious that this is the one thing that will be driving the demands for compute for the coming years. And of course, especially as of today, many of you have felt this like a situation of being GPU poor, not being able to even access like the NVIDIA hardware that has been pretty much required to kind of join this bandwagon this year. But of course, like in the coming years, there will be many other alternatives. Like all the clouds are developing their own hardware. AMD is developing their own hardware. NVIDIA is, of course, like very much like trying to maintain their lead and so forth. So it's going to be very exciting for the coming years. Now, overall, like where this all takes us, like kind of looking at these trend lines, is that it feels that it's absolutely the golden age of Python compute. So if you think about like where we came from, like in this scalable, horizontally scalable world, like we had things like Hadoop and Spark, and of course Dask was an amazing answer in the Python land if you didn't want to use these mechanisms. But now when we started moving in the cloud, I mean, like at least like we got a few more options. Many of us like use things like Amazon EMR, which was basically kind of a nicer version of Hadoop now, like running in the cloud. And I just wanted to give a kudos to this service called PyCloud that made it easy to run Python in the cloud already many years ago. I think that like that company was way ahead of its time. But there were these attempts to start providing better Python alternatives for many of us in this new world. And now, of course, like what has been trailblazing this new world of being able to do really demanding compute with Python are all these frameworks for like running like different machine learning models like TensorFlow and PyTorch and so forth. And what's remarkable about them is that there's an absolute crazy amount of brain power that goes into optimizing these frameworks and making sure that they leverage the hardware resources optimally. And that allows like all of us to do amazingly demanding compute in Python that absolutely like wasn't possible. I mean, it kind of surpasses what was even possible using C and C++ a few years ago. And now, like getting to the main kind of like a point of this talk is that in this world, and especially like for all of us using Python, it's kind of interesting that like what are the frameworks we want to use to kind of like really provide the compute substrate in this world. And when we started working on Metaflow 2017, it definitely was in this like a scaling the cloud world. Like we were at Netflix. Netflix is a big AWS user. We wanted to make it very easy to leverage the cloud resources in the cloud. So that like any data scientist could say that here's my Python function. I need like a big machine to handle my pandas data frame, or like now I need to train my model like PyTorch model, and I need 8 GPUs for that. And that's something that like we have provided since the very early days. But now, of course, like in this new world that is quickly emerging in this like a mixing and matching, there are like even more capabilities that Metaflow is providing, and I will talk more about that. And for those of you who maybe don't know Metaflow from the past, I actually like won't be spending any time going into details because Hugo will be going right after me in a few minutes, and like he will go into details about Metaflow. But suffice to say that the whole point of Metaflow is to think about the full stack of machine learning infrastructure that you need to build complete ML and AI systems, starting all the way from data and compute orchestration, all these like very basic questions that are very foundational. And also like thinking about this more like a human and organizational concerns, that how do you keep track of all the work, and how do you deploy these systems as a part of a larger kind of like a business environment. And of course, at the very top of the stack, there's the question that like, how do you do modeling? And of course, the idea is that Metaflow doesn't provide an alternative, and like absolutely like it would be crazy to try to do so, to all the modeling frameworks that are out there. But it really focuses, like you see from these triangles, that providing this foundational infrastructure, like especially focusing these questions of compute data, orchestration and versioning, so that like when you are like one of the data developers, data scientists, ML engineers sitting at the top of the stack, you can really focus on leveraging these frameworks, and you can get the compute resources when you need them. And again, I don't want to spend too much time on like going into details about Metaflow. Again, more about that in a few minutes. But the basic idea is that it's a very simple Python framework. Like the whole point is to focus on the developer experience that allows you to create end-to-end workflows, purely Python, no need to write any YAML. But let's say now when you need compute resources, you can simply say, for instance, at Kubernetes memory 64,000, I need 64 gigabytes of RAM to execute this Python function. And then like when Metaflow has been configured to work in your environment, that just like that function executes, and you don't have to worry about it. All the code gets packaged automatically. Even dependencies are handled as a part of this execution. You can say that I want this version of scikit-learn or whatever it might be, or like then you can also make this so that this workflow works as a part of a larger like workflow, and as a part of a larger system. Now, like going to the kind of main theme of this presentation, and like where the world is really going, is that there isn't one size fits all solution. So there isn't like a one universal paradigm like what we try to do with MapReduce, where you can say that, oh, I mean, just like follow this paradigm and suddenly everything will get scalable and everything will get high performance. I mean, honestly, that doesn't happen. Like the world where we are entering quickly is the one where there are very many heterogeneous workloads. Sometimes you need GPUs. Sometimes you need horizontal scalability. Sometimes you need a big box for like to handle like all your enterprise data in a DuckDB instance. And you need to be able to choose the kind of the right paradigm of compute very flexibly. And I will just like go through the kind of a few like a basic models what we support. And I think it's always worth mentioning that the starting point, the baseline, should always be that like you don't have to worry about scalability and performance. And I think that this is the big mistake that many of these like previous attempts, including MapReduce, have made, that there's the idea that, well, you kind of have to pay the scalability tax and the performance tax no matter what you do. And especially like for all of us coming from the Python background, like who are like very used to kind of keeping simple things simple, it kind of feels odd that like, why does it have to be so that like even the simplest possible things have to be complicated? And of course, that shouldn't be the case. But let's say if you have the most simplest like use case, whatever it might be, maybe you have a small amount of data, it's not business critical, it runs on my laptop, I want to keep life simple. What you can do is that you don't have to worry about anything. It's just like a write Python code as you always do, and then it just runs. And actually you can go surprisingly far with that, thanks to the amount of power that you just have on your laptop or a cloud workstation or whatever it might be. So also means that you can develop locally quickly because you don't have to worry about things that are maybe in the future. Now, the most obvious thing, like when you want to start scaling up, should be always this idea that, well, I mean, let's just like get more resources for the function. So let's say I have a big pandas data frame. It goes out of memory in my notebook because maybe it needs 64 gigabytes, maybe 128 gigabytes. So instead of changing anything in my code, I mean, why don't we just get the box in the cloud that has sufficient resources to handle that data frame? So for instance, in this case, I say that, okay, in order to execute this function, I need 8 gigabytes of RAM. And then I can handle pandas data frame, like as long as it stays below 8 gigabytes. And if I need more, I just keep increasing that number and I get bigger boxes. And as I showed you before in that graph, I mean, it's just amazing how far you can go with this approach. And thanks to the fact that this function only executes, I mean, or that the instances are only needed for the duration of this function, it can be very cost efficient as well, because you're not like launching a big cluster of these boxes that are just idling there. But AWS charges by second. So you say that, okay, now we need 128 gigabytes for 15 seconds. Like we use that, of course, like it might be that we have to launch the box there, but it goes down and like you actually like end up paying pennies for that. Now, what makes this vertical scalability approach even more exciting is the fact that now you can leverage these hardware accelerators like GPUs. And I can say that, well, actually, like give me the box with the A100 and like with 8 GPUs so that I can fine tune my large language model. I can fine tune the Llama 2. And now, again, like if you operate in an environment where you have these resources available, that's all you have to do. And now you can use PyTorch, you can use Hugging Face, like off you go. And like you just say that, okay, I mean, these are the resources I need. Now, another form of compute is this idea of a task parallelism, where we basically take the same data, but we perform two different operations for the data. And like a use case of this might be that, let's say you want to compare two different models, like where you have the same data set and like maybe you take a Llama 2 as a foundation model versus like whatever GPT-J or something like that. Or like maybe you have just like two different like algorithms that you want to run for your data set. And then you just say that, okay, I want to do the I want to do the step A and the step B, and maybe they even have different resource requirements. And like Metaflow now takes care of like running those things in parallel. And
sorry to interrupt, Ville. I'm sorry, but we've reached our time. And if people would like to switch over to the tutorial, I'm so sorry.
Yeah, I know. So yeah, I know. I mean, like, yeah, definitely you should join Hugo's talk. So yeah, I will just wrap up really quickly. So then this is the horizontal scalability idea. You can do things in parallel, or like just as a quick note, we also have this new feature that if you want to do distributed compute in a sense that like you want to have many boxes communicating, that is actually a new feature that was just released about a month ago. You should just check it out. So this was pretty much all I wanted to say here in this presentation. You should definitely join Hugo's talk next. What I also worth mentioning works in all clouds, also your on-prem instances. And now the best way to get started is actually to join Hugo's talk that is starting right now, and also like join the Metaflow community so we can answer any questions there as well. Thank you.